that way.
Good morning. Hi, I'm Dennis Akowski. I'm the science director here at Hudson River Foundation. Thanks for coming. We have a bunch of students today, right? Where are you guys from?
River College.
All right, great. Glad you're here. Today we're pleased to have Dr. Howarth of Cornell to talk to us today about nutrients and climate change. But before introducing Bob, I just have a couple of announcements. First of all, we have a December seminar that will take place on Tuesday, December 6th. Eric Schultz from the University of Connecticut will be here talking about feeding habits at early life stages of fish in the rivers in relationship to zebra mussels. So it's kind of an important topic for the Hudson that I hope to see some of you here to hear Eric's talk. Also, that I'd like to ask you to, if you've got a cell phone, put it on mute. What we found was that each of these lectures, we do tape them, and they're on our website, and we found that in going through, we get a lot of buzzing and beeping and so forth that interferes with the ability to hear whatever the speakers are saying. Also, we asked, and you guys were great about RSVPing, both here in person and folks on the webinar. By the way, we have about 50 people, we believe, that are viewing this now on via webinar. If you didn't sign up, that's perfectly fine, but we do have a sign-up sheet on the front desk. We'd just like to keep in touch with you, having a way to get back to you. So if you leave your name and address, and particularly your email address, we'll continue to send you information about upcoming seminars. Okay. So as I say, we have about 50 people on the webinar. For those of you that are on the webinar, if you haven't been on one before, you can hear us, so you can see the presentation. We cannot hear you. But at the end of the presentation, if you look on, I guess, the right side of your screen, there's an opportunity for you to ask questions to Dr. Howarth when he's finished with his talk. And usually that interaction with written questions goes very well. And so we'll get to that a little bit later. So as I say, we have Bob Howarth here, and Bob is the David R. Atkinson Professor of Ecology and Environmental Biology at Cornell. Bob, we were sort of reminiscing before. I've known Bob a long time, and I think of him as this young guy I've known for a few years, but those few years go back about 3 decades, I guess. Fortunately for the Hudson River and the Hudson River Valley, Bob has had a continued interest in working on biogeochemical issues within the Hudson River watershed and river. In particular, over the years, he's provided, he and his colleagues at Cornell have done quite a bit of work on nutrient inputs and processes that work in the watershed, in the river, and the export of nutrients to the ocean as well. But he's not only done that here in the Hudson River, he's done that all over the world in different rivers and watersheds. And so we have a nice, through his work, we have a really nice comparison of what the river systems are doing around the world regarding nutrients. Also, and I guess in his spare time, he gets involved in semi-controversial issues like fracking, where he's done some work. He's done quite a bit of work on the carbon footprint of the fracking process, just one other illustration. So Bob's got his hands in a lot of very interesting things. And now with his sort of understanding, gaining greater understanding of these watershed processes, he's looking at them in light of climate change. So which is really very, very interesting. I think all of us interested at the Hudson River Foundation, and we're going to hear about that, which is some ongoing work that we're funding here at the foundation. We're proud to have them here. And
Thank you, Dan. Do you want to, can you dim the first light? Is that possible?
we're going to get them all.
Okay. Well, thank you all for coming, and for those of you in the webinar, good to see you, so to speak. The work I'm going to talk about today is a work in progress. As Dennis says, it's work that's being funded by the foundation. We've made really good progress in some places. Other places, I'll give you where we are, but we're not quite there yet. Let me tell you the take-home message, just so I don't lose you from the start. There are a lot of aspects we could talk about in terms of where the nutrients are coming from. As Dennis mentions, we do a lot of work on that. I'm not going to talk too much about that today. I'm going to talk instead about the sensitivity of the lower Hudson River Estuary, New York City Harbor Estuary, to nutrient pollution, and whether or not that might change in the future in the face of climate change. And there are many aspects of climate change we could talk about. I'm going to concentrate on the freshwater flow down the Hudson River Estuary and how that affects the functioning of the estuary. So just a little bit of general background. If we have excess nutrients in an estuary, we can have a lot of problems. Excess algal growth. What do I mean by excess algal growth? Well, water can turn quite green. That looks a little scummy, but there are other problems associated with that. One is low oxygen events, either zero oxygen, anoxia, or low oxygen, hypoxia. And that's caused both by the algae as they decompose and sink and die, consuming oxygen. But in a system like the Hudson, even live phytoplankton can consume oxygen. When they're in the light, they're photosynthesizing, producing oxygen, but a lot of that exchanges to the atmosphere quickly, and then they can get mixed down, and they're spending a lot of time in the dark. They're still living organisms, can't photosynthesize in the dark, but they are respiring, and that can cause hypoxia pretty easily. Harmful algal blooms are common once we start to get excess algal growth, and harmful algal blooms are blooms of species which are toxic. They can be toxic to humans, they're toxic to other things. Toxins might bioaccumulate, which can be a public health hazard to humans. But it's also possible for them to produce volatile substances which are toxic. So if you were to get such blooms, say, in New York City, that would be a big issue, right? Loss of biodiversity, loss of habitat quality. Now, just for background perspective, this is a little bit old estimate I chaired a committee for the National Academy of Sciences longer ago than I should admit at the moment. But we said, and it's probably still true at the time, that 2/3 of the estuaries, coastal rivers and bays of the United States are either moderately to severely degraded from nutrient pollution. That was true in 2000 when this report came out. Still, by and large, true. Some places have seen progress, but not too many. Other places have seen degradation. So it seems to be about the same. So let's look at the Hudson. The Hudson River Estuary gets this amount of nitrogen per year, 290 grams per square meter per year. And if you're not used to thinking about that, that's a big number. It is the highest rate of nitrogen input to any estuary in North America, by far. If we compare it with Chesapeake Bay, where nitrogen pollution is known to have severe consequences to the bay, it's 20 times higher in the Hudson River Estuary. Boston Harbor, Long Island Sound, again, it's 20 times higher. Delaware Bay, it's still 10 times higher. So this is a heavily nutrient-loaded system. And yet, we don't seem to be seeing a lot of problems. And this is from the New York, New Jersey Harbor Estuary Program. They talk in general about fish kills and die-offs from excess algal growth and the low oxygen events that can happen. But they say this is a problem for Long Island Sound, and that the New York City Harbor Estuary is really not a problem except for some backwater tributary areas, perhaps the Raritan and things like that. And that's true. So nutrients are not currently a major problem for the Hudson River Estuary, even though the loads, the inputs are the highest of any estuary in North America. So why is that? Why don't we have a problem for this massive amount of nitrogen? And the answer is that the estuary is quite simply just insensitive to those inputs. Estuaries vary hugely in their sensitivity. Chesapeake Bay is an incredibly sensitive estuary. The Hudson River Estuary is incredibly insensitive. And there are probably a couple of reasons for this, but part of it is the fast flushing. Water is moving through that system fast. The phytoplankton are getting flushed out of there, ejected out about as fast as they can grow. We'll talk about that in some more detail. There are other things going on too. The water is pretty turbid, a lot of suspended particles in it. That means light's not getting far into the water column, and the mixing dynamics of the water are keeping phytoplankton somewhat lower in the estuary pretty commonly. So the light availability is low, combined with the fact that they're getting flushed out as fast as they can grow. So it's, you probably, quite frankly, couldn't have a city of New York's size sitting on this estuary for the last several hundred years without that flushing. Given the nitrogen loads getting in there, it would have been a stinking mess and people would have moved and done something else. So it's the physics which keeps the city happy with your water quality. So a little bit of background on that. Here's a table that we pulled together 10 years ago now, but it's still pertinent. So we're looking at the Hudson River Estuary compared to several other globally important estuaries. Over here, I'm showing you the mean residence time of water in the salty part of the estuary. We're saying it's about a day in the Hudson River. Well, you know, if a phytoplankton cell has plenty of nutrients, which they do in the Hudson, no problem there, and plenty of light, which they may or may not, then they will double their population size about once a day, right? If you're doubling once a day, but the water is moving out once a day, you can never really get big blooms. So you need to have longer residence times. If we look at, say, Narragansett Bay, it's 26 days, Chesapeake Bay, 230 days. So that's a huge difference. You can get a much larger response. Even though the nutrient load is 20-fold lower, they have a huge problem in Chesapeake Bay because of that long residence time. And in terms of what's driving that, if we look, it's a function again of the drainage basin and the area of the estuary itself, and I'm showing here the ratio. So the Hudson has a large drainage basin. You can see it there. It's going way up into the Adirondacks and off here into the Mohawk. Big drainage area, over 34,000 square kilometers. Relatively small estuarine area. So if you look at the amount of water basin that's feeding water into this estuarine area, it's 233 to 1. That's at the high end of a lot of other estuaries. Again, if we look at Chesapeake Bay, the ratio is 15 to 1. Relatively small, it's a huge watershed, but feeding into a large estuary. So not that much estuarine area per surface area. And on top of that, of course, we live in a pretty wet climate here in the Hudson River Basin. So we can look over here at the riverine discharge. That's the amount of fresh water coming down the Hudson and into the estuary. Keep silence, must be back there recording too. We don't get this amount of background noise when I'm talking, that's okay. If we look at the amount of discharge, the volume of water per area of estuary, the Hudson is at the high end of this again. Chesapeake Bay is far, far lower. So that again is a major part of sensitivity. And I should just say that this estimate comes from a fairly old way of estimating water residence time. I'm going to show you some better estimates in a bit, but the relative ratios there, relative residence times are all done in a similar way. So the Hudson is a very fast flushing estuary because of the physics of the system, etc. Okay, so that matters, and this is from some work that we did a while ago, and I'll get to newer work in a bit. But here I'm showing you for several times when we were measuring things out in the Hudson River Estuary off of Manhattan. The discharge, in this case, it's the amount of fresh water that's coming over the Troy Dam up near Albany, but it's representative of the entire fresh water that's coming down the river. Over different amounts of discharge, that should be cubic meters, not meters to 0.01. We're looking at the residence time of water in the estuary. And if the discharge, the fresh water coming down is larger than, say, 300 cubic meters per second, then the residence time is about a day or less. If we have less fresh water coming down, the residence time goes up. And the difference in symbols here are the tides. So the black triangles are neap tides or average tides, relatively low tidal amplitudes, and the open squares are spring tides when there's the tidal range is larger, and that makes a difference in the physics as well. But we get water residence times of up to 4 days or so of these lower discharges. That's still slow, but it makes a huge difference biologically because, again, phytoplankton might be doubling their populations once a day. If they can double several times in 4 days, you start to get some response. We also see a difference in terms of light penetration. So at the higher discharges, the amount of light Here I'm showing the 1% light level. So if you go down a meter or two at high discharge, 99% of light's been absorbed. There's too little light for photosynthesis. If you are down here at lower discharges, we might have a light penetrating down 5 or 6 meters. So that makes a big difference to the phytoplankton as well. And we put that together, and we measured in this past study the rates of primary production by the phytoplankton at these various discharges. At the higher discharges, we have pretty low levels of production, but when we have tide conditions, which lead to longer residence time, and the discharge is low, which is leading to longer discharge times, we have what turn out to be really high rates of primary production. So the estuary can respond when the physics allow it, but that's an unusual situation. So we had this conceptual model we've been working on for quite a while now, and we're trying to get more quantitative on it. I'll show you some of our new quantitative stuff. But the master variable here is the amount of fresh water coming down the Hudson River Estuary. When we have high flow periods, high discharge, it really doesn't matter what the tide's doing. The residence time is less than a day or two, and you simply cannot have high algal biomass or growth under those conditions. But when the freshwater discharge is low, and we have low tidal activity as well, the residence time can increase to 2 days and higher, and that's enough to give us high rates of production. If we have low flow and spring tide, high tidal activity, at least in the past, we still have short water residence time, and so not much going on biologically. Now we can see how this plays out not only in our own data, but also in the monitoring data collected by the New York City DEP. And I'm going to show you data collected here at station N1, which is right at the northern boundary of the city, the very northern end of the Bronx there. And so we're looking here from 1994 up through 2015, and I'm showing you two things. The top plot there is the log scale for both. The top plot is the freshwater discharge coming into the Hudson as measured by the U.S. Geological Survey, what comes over the Troy Dam basically. And the bottom line is chlorophyll. We measured the algal biomass in the river. This is from the City of New York's monitoring data. And if you plot one versus the other, this is the average freshwater discharge, and this is the average chlorophyll A, the average biomass. At higher discharges, the chlorophyll is low, but as the discharge is lower, we start to get into some reasonably high numbers. Are any of you used to think about chlorophyll numbers at all? Do these numbers mean anything to you? Probably not, huh? Okay, let me put in perspective now. What I've done here is overlay one way of determining water quality based on chlorophyll. This is from our 2000 National Academy of Sciences report. Basically, it says that if you're higher than about 15 microgram per liter of chlorophyll, this is conditions which are eutrophic. Water quality is degraded. That's an indication of that. This would be sort of in between, not necessarily unhealthy, but perhaps problematic. And this would be very low algal biomass for an estuary. So we can see that in general, algal biomass in the Hudson is low. Sometimes it gets into the sort of in-between state you might worry about a little bit. And in the past, we've seen a couple of events in months, but relatively few over that long time period where you might think the estuary is behaving in a eutrophic way. We can also look at the suspended matter in the estuary because that affects light penetration, which is another part of the story here. So same sort of plot. We're looking at the same freshwater discharge, but here are the City of New York's total suspended solids. And if we plot the freshwater flow down the Hudson versus the total suspended solids, we get a different pattern here. Fairly low at lower discharge. As the discharge gets higher, sometimes we see really high suspended solids. And that's probably simply that the high flow is associated with higher watershed delivery that's making it to the estuary. But this means that the water is more turbid under these conditions, light penetration will be less. We're going to also get less algal growth from that. So what I really want to address is the question of, will climate change affect the freshwater discharge and therefore the physics? Will that lead to changes in residence time, and what might that mean for phytoplankton production and biomass? And I'll talk a little bit at the end. Climate change has other consequences, sea level rise, obviously, but also delivery of nutrients from the watershed. And I'll mention that at the end. But what I'm going to concentrate now on is sort of the current input of nutrients, which is astronomically high. We're going to assume that's high. The nutrients are so high at current inputs that they could never be a controlling factor on production. You'd have to lower them a fair amount. So what's controlling the algal biomass and growth is totally the physics of residence time, mixing, and turbidity. All right, climate change. Any of you seen this? This is a cool figure if you haven't seen it. I'll talk to you through it. It's going to start here, going back about a century and a half, and we're looking at the global mean atmospheric temperature around the years and up through the years to the present, brought together by Ed Hawkins from the University of Reading in the UK. This will give you a sense of what global warming is like. So, and I said I had no animations, but now I do, and it's not going to work. Oh. Well, hold on. It's embedded in the PowerPoint. Usually this works, but it won't since I'm sitting here. Yeah, that's okay. Let's go back to the last. I guess I can do that. We'll go back to the last one. Okay, it's a cool graphic. If you go there and look online, it's worth looking at. What happens is we start 1850 and the temperature spirals around annually and it grows. And this would be the early 20th century, and the mid 20th century, and the later 20th century. And this is the last year. And he stopped showing this at March. But the bottom line is this year is the warmest year we've ever experienced. Last year was the next to warmest year we've ever experienced. And the rate of warming that we're seeing here is higher, faster than predicted by any climate model published up until this year. So the models have systematically been underestimating the rate of global warming, and you need to keep that in mind when I start talking about what global warming is going to do. I should mention, for those of you who are interested in the overall patterns of climate change, Jim Hansen, formerly of NASA and now at Columbia, put out a new paper 3 weeks ago saying that the reason for this unprecedented warming that the climate models haven't captured in the past is because the models have underappreciated the importance of methane in global warming. And the reason methane is going up sky fast over the last decade, and that's because of hydraulic fracturing and shale gas in the United States. Turns out that all of the global increase in methane over the last decade is from shale gas in the United States, and it's what's causing warming. That's an aside, but it's kind of pointed around. I work on that too, and I have to tell you. So this is actually out of the most recent paper by Hansen from 3 weeks ago, and they're looking at the climatic warming up through 2015, and they're doing a pretty good job of capturing that now once they accurately account for methane. And then they have some future scenarios, and I just want to point out that by the end of the century, the temperature may well be 3 degrees Celsius above the pre-industrial baseline. We're on target to hit 1.5 degrees above the pre-industrial baseline in 6 years from now, and we start to run about a 50-50 risk of runaway thresholds in the climate system at that temperature. So we're on the edge of some really disturbing trends. Now we are seeing some consequences already in the Hudson of the climate change we've had to date. And this is U.S. Geological Survey data again. We're looking from the 1950s up to 2015. And what I'm showing you here is the discharge, again, coming over the Troy Dam, Green Island data. The blue is the discharge on an annual basis, and the red is the summertime discharge, and we're seeing an increase in river flow so far. Now that's good if you're worried about water quality in the Hudson, because it makes it less likely to be any response to the nutrient pollution. Will that continue? Well, let's look at this in a couple of different ways. Here I'm showing you historical data in the 1980s, 1990s, and the last decade or so for the freshwater discharge coming down the Hudson River, and I'm putting them in various bins. So this is the bin of percent of time when the discharge is less than 100 cubic meters per second. This is the bin of 100 to 200. The sort of areas where we worry about water quality effects are down here. This is problematic. This is really problematic, probably, although we don't have a lot of historical information here. And what are we seeing? Well, back in the 1980s, this is annual time, between 25 and 30% of the time, the discharge is at that sort of level, sort of problematic. But by the 1990s, it was less, and by the 2000s, it was less. The discharge tended to be faster. Let me show you the summertime, since that's when we're most worried about water quality, more sunlight and things. Same sort of pattern. Back in the 1980s, 65, 70% of the time, we had this sort of discharge. It's gone, the frequency of these low discharge events has decreased over time. Again, the discharge has increased down the Hudson. That means the Hudson is less sensitive to nutrient pollution now than it was a decade or 20 or 30 years ago. Right? Yeah.
This is because of stronger rainstorms, right? Predominantly?
In part, yeah. But, well, there are a couple of things going on. It also has to do with the relative importance of snowfall versus rain in the Adirondacks and how that affects discharge and all. But I'll get into that in just a bit. But these are the historical data. So the estuary has probably become less sensitive to nutrient pollution. Now, coincidentally, in the 1980s is the time when we finally went to real sewage control throughout the Hudson. We were putting raw sewage into the Hudson in the 1970s, early 1980s, and we've increased the level of sewage treatment, brought down the biological oxygen demand that helps with the oxygen problems in the Hudson. And most people attribute the improved water quality of the Hudson to that lower biological oxygen, which it probably is. But we also would expect less of a problem from the nutrient pollution and algal production over that same time. And one of the things we're interested in doing, we haven't yet succeeded in doing it, is to tease apart those two influences, the better sewage treatment versus the change in hydrology. All right, I'm going to start showing you some modeling data now in a minute, and I just want to remind you the stream flow here, the discharge coming down the Hudson River. It's a balance between precipitation and evapotranspiration, and also the details of the hydrology in the watershed and type of precipitation do matter. So let's look at what we expect in terms of global trends. We expect the planet to be warming. This is several years old now from the Intergovernmental Panel on Climate Change. It's out of date, but still about the best out there. They're telling us within the next decade, we should be seeing these kind of surface temperature changes globally. In fact, they say we're on target to have a 1.5 degree average right out there across the entire planet within the next 6 years. So it's warming faster than this would indicate. We'd expect those sort of temperatures under different growth rates of greenhouse gas emissions by the end of the century. So pretty severe warming. We expect to see changes in precipitation with that. And again, both temperature and precipitation matter in terms of the discharge. And these are several model comparisons of the expected change in discharge in December, January, February versus June, July, and August. And the patterns here, if it's white, what that means is that the various models don't agree, and we don't really have a clue as to what's going to happen. If there's color, it means that there's about a greater than 66% agreement in the models, and if it's stippled there, it means there's more than a 90% agreement in the models. And those greener colors are higher precipitation, these are lower precipitation. So for the Hudson River Basin in June, July, August, there's no model agreement. And in the winter, it's probably likely to get rainy. Probably, with some uncertainty. And they also put out estimates of what would be expected to change in terms of discharge, the actual freshwater flow off the landscape. These are annual averages here. Same thing, if it's white, there's no agreement in the model. For the Hudson area here, they're predicting we'll get wetter, more discharge, but there's not particularly good agreement in the model. And this is a pretty crude global water balance, rainfall in, evaporation out by temperature. It doesn't account for some of the details and seasonality and things like snowpack. And snowpack matters. If the Adirondacks get a lot of snow that holds on to the water associated with that, obviously, in the winter, during spring melt, it seeps mostly into the groundwater and it will come out more in the summer, so it leads to more discharge. Then, if it was raining in the winter, in which case it just runs off in the winter, and the annual discharge actually goes down. Those sorts of things matter. So we've applied our own modeling, which allows us to look at more detail of that sort, and we've applied it to the Hudson River Basin. And we're dividing up the basin into these sub-basins, and we're looking both at past climate and to see how well we model, and at future climate so we can try to anticipate what the future might bring. And the model we're using is fairly simple in terms of its hydrology. It's this regional nutrient management model over NUMA, and the hydrology behind it's quite simple, which I like. So I can explain it pretty simply to you. The inputs are precipitation on a daily basis, 365 points per year, and daily temperature. And it deals with different types of land use in the watershed, and it's predicting stream flow or the freshwater discharge coming out. So, very simply, the model is putting in precipitation. If it's rain, it goes right into the soil as a function of land use pipes. If the soil has capacity for taking up water, it will, and some of that goes into this unsaturated zone, which eventually goes deeper into the soil. If the soil is saturated because it's been raining or there's previous snowmelt, then the new precipitation will simply run right off. So it's a confidence system. If it's below freezing, then stuff comes in as snow and it accumulates until the temperature allows it to melt, and it does the same thing. And we're losing water by evaporation and transpiration to the vegetation, which is a seasonal phenomenon. It does a pretty good job. We're looking here at past modeling. The dots there are the actual discharge data, and the blue line is our modeling for various sub-watersheds. It does a pretty good job of capturing the hydrology. And we've applied this model across many of the watersheds of the northeastern United States. And here I'm comparing observed water flow, observed discharge versus the model estimate. And the model does a good job in the past. So what about the future, and how are we looking at the future? Well, here we're looking at the latest Intergovernmental Panel on Climate Change, fifth synthesis from 2014. And there are various scenarios moving forward as to what the climate might be. These are different levels of greenhouse gas emissions resulting in different levels of carbon dioxide plus methane equivalency in these models, in fact. And we are looking specifically at these two scenarios, so a high rate of global warming, although in fact the rate of global warming has been faster than this rate to date, and a modest level of global warming where society really gets things under control, which I'm not terribly optimistic about at the moment, but I'll show you the results from both of these. This is from the Intergovernmental Panel on Climate Change, and then we're using this Canadian model to disaggregate that at some future time and say what happens on an average. Well, actually more than average, it captures the meteorology, right? We need daily precipitation, daily temperature data to drive the model. So we are estimating on a daily basis over about a 20-year period what the precipitation all would be under these sorts of future climates. And we just feed those future meteorological conditions into the model, and we come up with monthly discharge estimates. So here I'm showing you first predictions for summer temperature and precipitation, and we're looking at the different subbasins of the Hudson, and this is for the relatively modest climatic warming that I don't think we're likely to meet, at least not given current projections. So by the black is 2050 to 2059, and the red is towards the end of the century. We're expecting across the board about a little over 2 degree temperature rise by 2050 or so, and somewhat more by the end of the century. In terms of the precipitation in the summer, by 2050, it's looking higher in the upper Hudson, but actually lower in the lower Hudson, and by late in the century, probably higher precipitation across the board. And we throw that together to see what might be going on with discharge, and we get this, probably not much of a change by 2050, 2059 in the upper part of the watershed, but lower discharge in the lower part of the watershed, and by late in the century, lower discharge probably across the board. And then we look at the higher climatic forcing, and again, we are actually warming the planet faster than this projection so far. but the projections are that by 2055, say, we'll get about a 3.5 degree warming across the entire river basin and up around 6.5, 7 degrees across the basin by the end of the century. For precipitation, we'll get more precipitation, particularly in the mid part of the century, less so by later in the century, except for down in the lower Hudson. And we put that together in terms of discharge, and the expectation is that discharge will be decreasing over time. Even if we get higher precipitation, that higher temperature is going to overwhelm it because we get more evaporation, right? So another couple of ways to look at this. This builds on the data I showed you before, where we're binning the discharge into different types. So this is annual amount, and here's the summer months. Let's just look at the summer months because that's the real concern in terms of water quality. In this bin of no discharge to 100 cubic meters per second or less, we had some occurrences of that back in the 1980s, but none in the last several decades. We're projecting that by mid-century, it might be 35% of the time we'll be having those kind of discharges. And for the 100 to 200, which is also problematic in terms of water quality, we had high incidence of that in the 1980s, a lot less later. So again, the estuary has been less sensitive to nutrient pollution, but climate change will drive that right back up. So this is worse. That's with the low climatic forcing. This is with the high climatic forcing, which is probably a better prediction of what will happen. And we're seeing that by the end of the century, 40% of the time, we might be in this extreme low discharge event. And a large part of the time, most of the time, will be at less than 200 by the end of the century. So again, that affects the physics, the residence time in the estuary. It affects the amount of material coming down. It affects the water transparency, et cetera. One other way to look at that, this is the seasonal distribution in freshwater discharge coming down the Hudson for the 1980s, 1990s, and first decade of this century, with the actual variance, and obviously it goes down in the summer. But in recent, over the last decade or so, we see commonly 200 to 300 cubic meters per second in the summer. Our future predictions here with the higher forcing are that it's going to typically be down in the 100 cubic meters and sometimes lower, sometimes down to 50 cubic meters per second, which we have not seen before in the Hudson. So going back to the slide of how chlorophyll phytoplankton biomass compares with freshwater discharge from the historical monitoring data, recent summers have put us in this sort of trend, which by and large keeps you at lower phytoplankton production most of the time, occasionally higher. Future summers are going to be here, sort of outside of the realm that we see, but we think that will lead to more water quality issues. So our attempts at figuring out exactly what that's going to do is what? Still a work in progress. I hope to be able to come here today and show you something really exciting, and what I can only do is show you some teasing and explain why progress on this is taking us longer than we think. But we're using a model called the Regional Ocean Modeling System to look in detail at the response of the physics and biology of the estuary. Just going to show you some physical data today. So we're modeling the entire system from here offshore the New York Bight into the lower estuary, and then through here into the lower Hudson, the Hudson River Estuary per se, all the way up to the Torrey Dam. And I'm going to particularly show you today the Hudson from about upper Haverstraw Bay down to right up here off the bat. Just a word on the model. This is a model that was designed to work with continental shelves originally. It's a three-dimensional physical oceanographic model that throws biology and chemistry on top of it. So it's a series of boxes, and water just moves from box to box, up and down, and sideways, depending on density differences in a short time span. And we have a pretty fine structure here. We're looking at the Hudson on 10 meters by 10 meters horizontally, and half a meter by depth. So a lot of boxes, a lot of computational power, problems. Problems is the word that comes to that in a minute. Here's the sort of output we get. So I'm showing you here a time when we're looking at 500 cubic meters per second. That's about the annual average at the moment. And we're looking from 60 kilometers north of the battery. We're right at the battery here, which is the lower end of the Hudson River Estuary. That would be upper Haverstraw Bay down to the battery. And we're looking at spring tides and neap tides, a strong tide and a weak tide. And this is the salinity pattern. So almost fresh water up there, down to about 2/3 of salt water here. And again, almost fresh water there. A little bit saltier down here. You can see a lot more stratification, more density gradient on the neap tide than on the spring tide. And I'm going to overlay where the phytoplankton can actually grow on this, just to give you a spatial sense of what's going on. So the little green boxes are the area in which the plankton of concern can actually grow in the estuary. And basically, they won't grow at less than about 5 to 10 parts per thousand. This more freshwater portion, we're dealing with freshwater phytoplankton. They die off as the water gets saltier. So if we're going to have a water quality problem from phytoplankton in the Hudson, it's going to be the ones that are marine species, or estuarine species, and they can only grow once the salinity gets about at least 5, but more like 8 to 10 parts per thousand higher, and they need light. So what I'm showing you here is for the spring tide and the neap tide, the depth over which phytoplankton can grow with enough light, and the salinity range in which they can actually grow. Okay? Pretty small part of the estuary. And this is showing you the age of water out of our model output at 2 different discharges. So 200 cubic meters per second, which is not as low as we think it's going to go, but it's at the low end of what you tend to see now, and 500, which is sort of the annual average. And the numbers here are the age of fresh water as it enters upper Haverstraw Bay and mixes with salt water and moves up. So I'm showing you with the arrow the area in which phytoplankton can actually grow and become a problem in the Hudson. And for the phytoplankton in the light zone of the estuary at these higher salinities, under this discharge, they have about 4 days before they're ejected out. And at this higher discharge, from there to there, they have about a day and a half before the start to get going. So that agrees reasonably well with what we were doing with the cruder modeling before. So what I'd like to do, or what I'd like to have been able to show you today, is what happens at 50 to 100 cubic meters per second, because that's where we are. But it turns out that we need to run this model. We're running it on a supercomputer, actually, and it needs to come to equilibrium, and it takes us more than a day to make a model run, as it's currently configured. And we can't do any better than running it on a supercomputer, so we need to figure out how to reconfigure it. At higher discharges, it comes to equilibrium quickly, but lower, it doesn't. So we don't really have an idea of what the residence time is yet, except it's going to be much longer than 4 days. So let me tell you what the next steps are in our current funding, what we will do within the next 6 to 8 months, and then what we are thinking about for the future. I think instead of looking just at the residence time, which turns out to be more computer intensive than we realized, we'll step back and explicitly model phytoplankton production, which for reasons I don't entirely understand, but my colleague John Wilkin, who's a physical oceanographer, tells me is correct, is far less computer intensive. So we'll step back and do that. We're going to continue to assume nutrients are always prevalent. We're going to look explicitly at the oxygen dynamics, and the controls we're going to look at are the residence time, but also light, which is a function of both the mixing depth and suspended sediments. And I'm optimistic that we'll be able to get some estimates of that within the next 6 to 8 months. In the future, if the Hudson River Foundation is kind to us and allows us to continue working on this, we'll continue to look at modeling the actual production and the oxygen dynamics under these future climate scenarios, but we want to look at reducing the nutrient input. In our original modeling right now, we're assuming nutrients are high. They are really high. No one's talking about putting them down. And we'll look at some other effects here in a minute, too, that I'll talk about. But I want to point out that if you have really bad harmful algal blooms, really bad excessive algae, people get upset. And this is in the Belgian coast, there off of the Howarth River Estuary, right in the mouth of the Howarth River Estuary. This is not snow. This is summer, and that's algal foam coming up on here, and it's giving off smelly, toxic gases. It is terrible for the tourist industry, not so good for people living in the city. Now, I'm not in any way suggesting that in the future we would get this bad of a problem in New York. But we could well get a problem that's a lot worse than we've seen historically. And people might start demanding, in addition to fish kills, the estuary could stay, as we talked about, right? So if so, what would happen? I'll get to that in just a second. Just to remind you that in the past, the low oxygen events in the Hudson were probably primarily from the biological oxygen demand from sewage. We took care of that largely in the 1980s, but going back to the 1970s, our estimates are that about 2/3 of the oxygen problems in the Hudson were from sewage and maybe 1/3 from phytoplankton. Again, those were lower discharge times than we've had in the past couple of years. Currently, we're guessing that the biological oxygen demand from sewage is about 20%, and phytoplankton is about 80%. Oxygen is not a huge problem now, but we think it could become much, much worse in the face of this change in physics. So that might demand that you start to reduce the nutrient load, right? Well, this is where we think the nutrients are coming from. About 23,000 metric tons per year of nitrogen from sewage, some from combined sewer overflows and stormwater, and about 18 from the Hudson River Basin non-point source stuff, for a total of about 43, big number. And I just want to throw out, I know no one in New York is thinking about this, but you might start to think about it if the estuary starts to sink, like it was in Boston Harbor a while ago. And Boston, back, a decade or so ago now, moved its sewage effluent from the inner harbor to offshore, about 15 kilometers, precisely to get rid of the massive algal problems which are in there. And I'm suggesting that New York City might consider doing that on the 20 to 30-year time period in the future if water quality gets excessively bad. That would reduce this part. You would still have a large nitrogen load just in the non-point sources. Boston was lucky because it has a very small watershed. They got rid of their sewage and solved the problem totally. If New York develops a problem, sewage is not the total problem. Non-point sources are as well. But this goes back to our projections of freshwater discharge. If the freshwater discharge goes down in the future, so will the non-point source nutrient increase. And we don't know exactly how much yet, but we can model that. My guess is that with these sort of future changes, the non-point source nutrient load in the Hudson will be cut by about 2/3. We haven't yet modeled that explicitly. We will, and I just want to point out we can do that. We can use RENUMA and ROMS to estimate what the response of the estuary would be to the future change, but also if we got rid of the sewage input. And this is just our RENUMA model. I showed you the physical aspects before, but what we've really fine-tuned it for is looking in detail at the nitrogen chemistry and nitrogen flows. We do a pretty good job of doing this, and we can certainly look at what the future climate changes do to that as well. So the final thing I want to mention is sea level rise. And sea level has been rising. This is the average change in sea level rise right here at the Battery in New York. It's been going up at about 2.8 millimeters per year. That's not terribly high. The worry, and this becomes increasingly likely after we hit 1.5 to 2 degrees Celsius, if we hit 1.5 degrees, there's a good chance that the Greenland ice sheet will plain melt. And once we hit that, which is about 6 years from now, the Greenland ice sheet won't melt instantly, but it will be at a tipping point where if we start to cool the planet, it's inevitable that it will melt. And it might take a century to melt, but it will continue to melt. The Antarctic ice sheet is trickier, but if we hit 2 degrees Celsius, it too is very likely to melt, again, irreversibly. The Greenland ice sheet will add about 6 meters to sea level rise, and the Antarctic ice sheet will be about 60 meters. That won't happen instantly, although the time frame over which this will become irreversible is the next decade to 2 to 3. But the time over which it plays out could be up to 400 years. It might be 100 to 200. We don't know. However, by the end of this century, most people think we're going to see a melting of perhaps 1 to 2 meters. So what will that do to the Hudson? This just shows the elevation of waters, of land, that is, in this general area and near the Hudson. And you can see that the Hudson, lower Hudson here, that's the battery, going up the Hudson, sea level rise is not really going to flood the land because the land around it's pretty high. In New Jersey, you'll lose some area of land here, and the Hudson Estuary will expand, and the lower harbor area here will expand somewhat, but relatively relatively little. And I just want to point out that we can easily make this change in ROMs. We have the basic bathymetry of the Hudson in there. We can simply add a meter or two to it and continue to run the model until it does. And it's likely to decrease the water residence time, which is a good thing, I suppose. So, my conclusion. Hudson is extremely highly nutrient loaded, the highest nitrogen loads for any estuary in North America, and yet we don't tend to see much trouble from this. The phytoplankton production in biomass over the past is strongly tied to the freshwater discharge rates. Low freshwater discharge, the residence time in the estuary goes up, phytoplankton production goes up. That freshwater discharge has been increasing in recent decades because of climate change, because of higher precipitation, and that has probably led to improved water quality. And again, we want to explicitly look at that versus the BOD changes and see which has been more important in the future. But climate change in the future is likely to change that and reduce the discharge during the summer, perhaps leading to a very serious degradation of water quality, in which case it might make sense to do the Boston situation and think radically. I'm just throwing that out there for the management community, which I'm sure has not yet thought about it. So I want to thank the Hudson River Foundation, which has funded us off and on, but for many years, starting in 1984, which I appreciate. And the work I've just talked about, all of these people were critical to it. Dennis Swaney did most of the watershed modeling I've talked about. Sam Nadell and John Wilkin did the oceanographic modeling I've talked about with help from Roger Geyer and Dave Ralston. Bong Gi Hong used to work for me and did some of the watershed modeling down to the state of North Carolina. And Bo Raynham from the city DEP has been very helpful in providing us data. So thank you.
Questions?
Yes.
Now, question about Morgan Abbey Park.
Thank you.
Yeah, my name is Wen Gao. I'm a professor at NJIT University of Technology. Just have a quick question. You did based on your model, you said that due to timing moving, so we're looking at a decline of water discharge. So basically, we're going to have a shorter average residence time. And my question is, were you able to identify some non-point sources for nutrients? And are you able to predict what the nutrient level will be?
Yeah.
That's the goal.
The question is, have we looked at and predicted what the non-point loads are and what the effect of climate change will be on that? We have, in the past, modeled the non-point source nutrient inputs from the Hudson, and it turns out I actually took a slide on that, I think. Can you go back a couple? Maybe I can go back. Probably can't. Some of your control. Go back. Oh, I don't know. Can I do it? No, I can't. Yeah, here. We've estimated for nitrogen, it's about 18,000 metric tons non-point source from the watershed. With a large part of that, about 40% of that would be from the Mohawk River Basin, which is fairly agricultural, and about 40% is from the lower Hudson, which is largely suburban sources, and a small part from the Adirondacks upper Hudson. So sewage is more important. We have not yet looked at what climate change will do to that. We'd like to. That's not difficult for us to do, but we haven't yet gotten around to doing it. My guess is, as I say, the lower freshwater discharge, that number will go down, and I'm guessing it will go down to the neighborhood of about 6. So if we're right, climate change will make the whole system more sensitive to nutrient pollution, but it'll put this from 18 maybe down to 6. We'll still have too many nutrients, but if you divert the sewage offshore, then you may have a relatively low nitrogen-loaded system that could be quite nice at some extent. But if you're building up seawalls to protect Manhattan anyway, why not do the sewage rate?
I I've got a question, Bob. These numbers are for basically the watershed above, it includes New York City and above, it doesn't?
Yes.
Doesn't include the rest of the watershed for the New Jersey side of the harbor?
It does. Yes, it does. It includes the entire watershed. Yeah. You know, they're model estimates from our renewal estimates. So what we can do, the only place where we can really compare that with good monitoring data to figure out if we're right or not is at the Green Island monitoring station. So we do a good job of predicting what comes together from the upper Mohawk and the confluence of the upper Hudson. That comes together, and we do a good job of predicting that. We're modeling what goes on in the lower Hudson, including New Jersey, and the monitoring data don't allow us to verify at all. Yes?
What's the status of sending pollution out to sea by pipe? One time it was done, then environmentalists said it's no good, so they don't do it anymore.
Yeah.
So what's the status now in New York City?
Well, do you want to speak to what's going on now, Tom?
Rick, do you want to?
Yeah, I can try, but we have experts who are.
Got Rick Ballard from EPA.
Sure. The 14 sewage treatment plants in New York City and the New Jersey plants continue to discharge where they discharged historically. There's been little to no change in discharge rates, I think, as far as I know. You might be referring to the fact that previously sewage sludge was
It's one thing that's sent out to sea.
And sludge used to be shipped offshore by barge to, 106 miles offshore, I believe, and dumped. And that's illegal and stopped quite some time ago.
It was also pipes. That was all stopped.
Yeah.
I don't know what they do with the sludge these days.
Yeah, it's upstate New York.
It seems pipes make a lot of sense to me.
Well, and that's what I'm suggesting the cities start to think about. And it's a fairly radical thought, but Boston did it. It resulted in a huge improvement in water quality in Boston. I mean, if you get to the thing, the reason environmentalists don't want you dumping stuff on the shelf, I think is fairly obvious. But if you have the same amount of effluent, putting it 12 to 20 kilometers out in the New York Bight, where the physics of moving water all over the place, makes more sense than putting it in the East River or the Hudson River, to me.
With the sewage effluent, I assume the vast majority of this is New York City sewage effluent.
Yes.
And that's so near the very bottom of the estuary. I would think that would reduce, that would have less impact than if the bulk of the sewage was coming from Albany or somewhere upriver.
Absolutely.
I would think that the impact of all the sewage effluent is reduced because it's almost at the very bottom of the estuary.
98% of that number is at the bottom of the estuary. You're correct. And the water's flushing it out, so it's getting out here fast. And so it's having relatively little impact. Yeah. Absolutely. But, again, if the estuary flushes on a time scale of a week to 10 days to 2 weeks instead of 1 day, then it's going to sit off here.
Well, it's going to certainly be out from New York City in less than 1 day.
Well, I'm suggesting not.
Even from New York City into...
Yeah, I mean, if you look at the... Sorry. I mean, New York City is what, up to about 18 kilometers, something like that? So New York City is in this part of that dimension. This is the battery, that's the northern boundary. So under a discharge of 200 cubic meters per second, it would take 3 days, 2 to 3 days for it still to get out of the city. And we don't have the model runs yet with the lower discharge rates of 50, but my guess is that that's going to go up to a week or so. I mean, that's what the preliminary runs look like, but they're not coming to equilibrium. So it could be, it's at least a week, it could be 10 days. And that's a long time for stuff to sit there.
Just want to offer an observation. So of the roughly 1,800 milligallons per day of sewage that comes from the 14 New York City plants, about 700 milligallons per day of discharge into the Long Island Sound with an export. That way, those 4 plants do have nitrogen nutrient removal.
Right.
The rest of the plants don't. On the New Jersey side, I don't know the total numbers off the top of my head. It's certainly less, but it's still high. I think it's at least, I think, 1 billion gallons per day, and there's no nitrogen removal on the New Jersey side. So
yeah, and the number I'm giving you there for the sewage is the stuff going into the Hudson, but does not include what goes into Long Island Sound or the East River.
Right. I'm just looking comparing to if you look at the population of New York City, not all of it is.
No, exactly.
And unfortunately, that's not in
of that number I gave, I think it's about, as I say, it's 98% of it is the lower Hudson area, but I think it's 3/4 New York City discharge into the Hudson and 1/4 New Jersey discharging into the Hudson. There's not much nitrogen control in either of those.
That's correct.
The nitrogen control is focused on Long Island Sound, which makes sense because that's where Long Island Sound is a sensitive system, Hudson's not.
And Jamaica Bay, so of course that falls also in Jamaica Bay, which I think becomes part of your boundary condition, but it's not discharged to the harbor.
And we did include it in there, yeah.
And those Jamaica Bay plants also have or will have nitrogen.
We got a couple of questions, Bob, from
Okay.
the webinar. I think at the middle does the heavy use of herbicides. Looks like, is that the first question?
Yes. Does the heavy use of herbicides, pesticides, and fertilizers in land and landscape management practices have any impact on the nutrient load of the Hudson?
Well, we haven't looked explicitly at the herbicide issue. To say that the Mohawk River Basin is a moderately heavily agricultural basin, and the nitrogen and phosphorus loads from there are moderate for a rural landscape. They're among the highest in the state of New York, and they've become greater over time. So I think we could do a better job of reducing those, and there are people thinking about how to do that. I work for the State of New York's College of Agriculture and Life Sciences at Cornell, and we are worried about how to reduce generally the non-point source impact from agriculture in the state. There are ways to do so.
If we go back to starting with given that, maybe you could read that, Bob. I can't.
I'm struggling with my glasses. No, I can't.
Okay, great.
Thank you.
Given that your data that the model is using only covers 35 to 40 years, if you increase your data set to 200 back to medieval warm period, you see very significant long-lasting droughts. Could you run your model to see how severe future discharge droughts might be?
Yes, I mean we can, but what we're doing already is on the edge of guesstimating, right? I mean, we can go back and try to estimate what the discharge was in the geological past, but I don't really know how to do that. And I have not seen any estimates for the Hudson, so I don't think actually we are not proposing to do more in terms of the future projection of the discharge than we've done already. What I'd like to do is do a better job of understanding what that does to nutrient flows and interaction with phytoplankton moving forward. Because you should take these estimates with a grain of salt. But I think you should say that the direction's probably right. The discharge will probably go down because the temperature influence is going to overwhelm what happens with the precipitation.
Someone here has 2 questions. What will be the effect offshore of increased nitrogen discharge? Also, is there any prospect of increased nitrogen release as soil pumps?
Okay. In terms of offshore, we're actually running our model out into the New York Bight. So I'm not showing you data for that yet, in part because we still haven't gotten the residence time in the Hudson down exactly as I'd like. But we will have estimates for what it does for the residence time and mixing throughout the New York City Harbor Estuary into the lower bay and into the Bight. And we will be able to look at what the consequences of that are for nitrogen. The residence time in New York Bight itself is pretty slow. There's a massive longshore injection of water through there. And so historically, there's been a debate about whether the load from the Hudson has had an influence on water quality there or not. There were hypoxic events historically in the 1970s, 80s, something like that. And whether or not that's tied to nitrogen from the Hudson has never been resolved. But we'll be able to model and test that. We're not there yet.
Here's another one. The estimate of 80% of the DO impact being attributed to N seems to be at odds with previous work done by Heck. Have you compared your model projections with those done by Hydroqual for EPA?
Yes, we have to some extent. We need to do more of that. I don't believe we're in major conflict on that, but we can sit down and see. The major conclusion in the past was that the BOD was the largest source. I think the SWEM model, which has been used in the past, probably was underestimating the phytoplankton contribution in the 80s. I think it's done a better job more recently, but I think the phytoplankton production's been less than because the discharge has been less than. So, and I'm not sure, I have not seen data for interdecadal comparisons from SWEM. I'm not sure that they've addressed that, which we're trying to do. Yes?
Hi, I'm Melissa from the River Project. I was wondering, with sea level on the rise and potential high tides, would that increase flushing in the lower Hudson around New York City?
Yeah, I don't know. I mean, you'd think so. I mean, if you actually get a 2 meters deeper water out there, that's, you know, right now the water out there is about 17, 18 meters deep. So if we deepen it by 2 meters, that's significant, and it'll probably, it's got to affect the physical, probably result in faster flushing. And also broaden the estuary because you're going to lose some of New Jersey. But we haven't yet modeled that. That's in the future.
I see a question I can answer there. Where somebody asked, where is the St. Valley wastewater treatment plant discharge? And right outside our window, I guess offshore Bayonne, Robbins Reef, is that correct?
Upper New York.
Upper New York.
Can you talk a little bit about atmospheric deposition of nitrogen and how that's changing and predicted in the future?
Yeah, the question is about atmospheric deposition of nitrogen, how it's changing, how it might change into the future. The atmospheric deposition of oxidized nitrogen has been going down over the last 20 years throughout the river basin, which is a success of the Clean Air Act, right? Less oxidized nitrogen pollution, less deposition, and it's gone down on average by a factor of about 2, say for the entire Hudson River basin. So that's good. Deposition was the dominant source of nitrogen in the upper Hudson basin, so the Adirondacks. Probably still is, but it's getting marginalized there. It has not been the major source in the Mohawk, where agriculture is dominant anyway. So it's probably, for the total non-point source, the estuary, probably the change in oxidized deposition has decreased the non-point source load by 3–4%, something like that, just because there's so much else going on. But it's important in the upper Hudson for sure. In terms of ammonium deposition, that has increased, and that's largely a result of more animal agriculture in the Mohawk River basin. And that's probably resulting in some increase in the flux down the Mohawk. And I should add that ammonium deposition here in the city of New York is extremely high as well. It's coming from car exhaust, bus exhaust, diesel stuff, plus the sewers. And ammonium deposition here is about as high as it's been measured anywhere. Hudson River Foundation kindly funded us to look at that a few years ago. It adds to the street runoff and the combined sewer overflow, but it's dwarfed by the sewage still. So,
can you talk about how that number, that's included in your non-point source number, and will that number stay constant, or how will that change? You predicted with low flows that the non-point source will go down, but how was the atmospheric?
The ammonium deposition is not included in what I showed you. The oxidized nitrogen is. The number I gave you would have been for circa 2000, so we have not included the update of that yet. We're submitting a pre-proposal to the Hudson River Foundation on Monday. If my university decides to go with my request, and if the foundation looks kindly on that and lets us submit a full proposal, one of the things we want to look at is trends in the non-point source deposition and how that might interact with future climate. The thing we have difficulty with, I don't know how to anticipate what the land use pattern will look like 50 to 100 years into the future, and that's critical. But what we can do is say, if you take static land use, what will happen with climate change on the ground?
Recently, I was at a lecture on Indian Point where the speaker talked about the tremendous volume of water that's taken in and heated up and sent into the Hudson.
Yeah.
Does this have any effect? How does this water affect what you're talking about in terms of volume?
It's not included in our model.
Has it really killed any fish to any extent?
Well, I'm not up to date on that literature, let me say that. But in terms of the physics, I'm not quite sure where Indian Point is spatially in here. We don't include it in our model. I don't know if it would have an influence on the physics or not, and I don't know where it is. Does it have any effect? 50? Okay, so through there. So I honestly don't know. I mean, if it's a thermal effect, it's probably.
Who can I speak to who might know?
You don't know?
I'll talk to you later.
Yeah, I honestly don't know.
I'll talk to you later. Probably the DEC would be the best host, but I'll talk to you afterwards.
This is Tony Emily from NIT, and thank you for the very enlightening talk. And
Thank you.
Based on your model, you predict that in long term, the discharge of Hudson River will significantly reduce. So do you think this decrease of discharge will lead to slow down the flow rate of the river?
Yes, so the question is, when the discharge goes down, do we think it'll affect the flow rate of the river? And yeah, I mean, discharge is a measure of the flow of the freshwater part of the river. So what we're saying is, yes, the freshwater river will slow, and we will see, if the model is anywhere near correct, and I think it probably is given the rate of warming you expect, we may see time periods where it's as low as 50 cubic meters per second. That's 4 to 6 times slower than what you'd be seeing in summertime now. And so that's coming through the freshwater part of the Hudson. Once it hits the estuary, we are saying, yes, it'll also slow the mixing of the water there and the flushing out. And exactly by how much, we don't know, because we can't get the damn model to come to equilibrium yet. But the non-equilibrium, the model's crashing at about 7 to 10 days, which tells us the residence time will be longer than that. So we know that. How much longer, I don't know.
So do you think that how would you envision this decrease of flow rate impact on the contaminant space in the river? For example, we have the legacy contaminant like PCB, and also we have the emerging contaminants like the pharmaceutical compounds which flush from our drain. Mm-hmm. And how would you envision the flow, the reduce of the flow rate on the contaminants?
Question is, how will the change in flow rate affect contaminants? And I honestly don't know. I mean,
do you think they may stay the because if you envision this river as a bioreactor, will this slower flow rate will make these contaminants stay in the river for a longer time?
Make it stay longer.
They will interact with the wildlife for a longer time and also equilibrium with the sediment.
Well, keep in mind that I'm saying things are going to slow, but those are still fast rates, right? I mean, it's still water moving all the way from Albany, the Green Dam, down to here. It's still going to be relatively fast, and the residence time in the estuary, if it really goes up to 10 days, that's a lot longer than now, but it's still a short time compared to most estuaries. And Chesapeake Bay is 260 days. So we're still talking about a rapid flushing system. It's hard to avoid that because it's such a large watershed compared to the actual size of the receiving water body. So we're not saying it's going to become really stagnant. It's just going to become more stagnant on a time scale that's critical to the time scale of phytoplankton, but I don't know about the bioreactor timescale.
Another question from the webinar. Are the areas WWP mainly located in low-lying areas at greater risk of accidental releases due to sea level rise and therefore increasing nutrient load in the waterways?
So the question is, when we lose these areas because of sea level rise, is it going to affect the nutrient load from what, sewage? Yeah. I mean, presumably the sewer authorities will do their best to keep up with this, and I mean, a large part of the sewage is pumped already, I believe. It must be, and so, you know, you put in tide gates. Most of the combined sewer overflows for New York City, I've actually seen the majority of them up close and personal. Most of them have tide gates on them, and so they're somewhat protected, and you pump. I think the city, I mean, there'll be problems with flooding, but I don't think that's the biggest problem. I mean, a meter or two by the end of the century is dramatic compared to anything we've seen in the past, but it's a long time to deal with it too. I'd be more worried if we lose the Antarctic sheet about 60 meters. 60 meters is going to be tough for the city of New York to deal with, but that's more probably on the time scale of 150 to 400 years.
And one more. Do you have data on the water quality to the areas where there's wastewater treatment discharged into the river?
No, I mean, we're using primarily the city of New York's monitoring stations, which are out in the main stem or some of the tributaries, but not right at the outflows. There's pretty good dispersion in the immediate discharge areas.
Can you talk a little bit about the impact of the lower discharges and sea level rise on community in the Hudson, and obviously, I think there's more in the salt dropping, and also changes in people emission?
Yeah, with lower discharge, the salt front will move further upriver, and actually the one you were just on, well, well, back one more the other way. Oh no, I'm sorry.
I guess the one other aspect of that influence phytoscience and production in terms of within the Hudson?
Within the saline part of this, yeah, we think it will increase production a lot because, you know, again, if the water is moving and the phytoplankton cell is only there for a day before it's washed out, it's doubling its population on a day. It just can never grow. If it's allowed to have 10 doublings over 10 days instead of one, that's a huge difference. Although the physics, how deep into the water column it gets mixed is important too, which is why we're going to give up on the residence stock calculation per se and move into explicit modeling of the phytoplankton behavior. The salt wedge will move further upriver. We probably do have some runs already which show that, but I don't show it here because we've only run to the upper part of Tavistock Bay, which is already a little salty. Historically, you'll in drought conditions, you do get salt water going up to the bottom waters as far as Poughkeepsie. And I would imagine it'll go further north than that.
But that's something that'll be an output of the model.
Yes. Yeah, we'll be able to get it. Yeah, absolutely. A lot of good questions.
Anybody else? Okay. If not, thank you, Bob.
Thank you. Thank you for coming.
As a reminder, if you haven't signed in, please do so at our desk, and hopefully we'll see you back in December. Thank you very much. Thanks.